In this video, we are going to learn how to analyze electric circuit using Kirchhoff current law and Kirchhoff voltage law. And before we do, I would like to define a few terms, and we are going to define what we call nodes, right? So we're going to define nodes. I define a node. So as we are going to, there are two kinds: simple node, right, and essential node. So simple nodes and essential nodes. Okay, so we're going to define what we call branch, right? Define a branch. Okay, and we are going to define loops. So define a loop. So we need, we need this to formally define what the Kirchhoff current law is, right? So for short, for Kirchhoff current law, right, we are going to call it KCL, and Kirchhoff voltage law, okay. So we are going to, for short, we're going to call it KVL. Okay, so why do we really need to know this laws? So these laws are essential, right, for analyzing and designing electrical circuits. And this law provide also provide systematic method to find current and voltages in an electric circuit, and they're very foundational, right? Laws they help really to solve real world problems, and they have plenty applications in electronic and power systems and many more systems. So we are going to define what we call a node. So the first topic that I would like to introduce will be the Kirchhoff current law. Okay, so one, we are going to talk about Kirchhoff current law, which is KCL. Okay, so what is a node, right? So this a node, right? So a node, okay, so is a point in a circuit. A node is a point, right, where two or more elements are joined. Okay, so now I'm gonna define an essential node. So an essential node is a point where three or more elements meet, are joined, Okay, and that's an essential node. A simple node right is a point where two elements are joined. Okay, so I am going to use this term, essential nodes, simple node, or just a node. Okay, so to define to give the definition for Kirchhoff current law and Kirchhoff voltage law. So, but we know that, so one of the fundamental conservation principle in electrical engineering, right, is that a charge cannot be created or nor destroyed, right? So one of the fundamental conservation principle in electrical engineering right is that so a charge excuse me, a charge cannot be created nor destroyed. Okay, so this is the principle that really guides the Kirchhoff current law. So it says that the sum of current, so KCL, says that sum of current flowing to a node or entering a node, flowing into a node, is equal to the sum of current flowing out of that node. So flowing out of that node. Okay, so if I give you this example where we have this node, there's a point where, so let's say this is point A in a circuit where we have branches. Okay, so let's say this is I1, this is I2, I3, and I4. Let's say we have another one, which is I5. Okay, so at this node, says that, right, so at node A, we have some of the current entering or flowing to the node is I1 plus I2 plus I5 equal to the sum of the current that I live in the node, which is I3 plus I4. So we can write this as I1 plus I2 plus I3 minus I3. Oh, this is I5 here. Minus I3 minus I4 equal to 0. So when we have I1 plus I2 minus I3 minus I4 plus I5 equal to 0. So, well, if you agree with me, this, right, we can rewrite this, the definition as this is an algebraic sum, right? So this is an algebraic sum. Okay, so we can redefine our KCL as the algebraic sum of current flowing into a node. So the algebraic sum of current flowing into a node is equal to 0. So flowing into or flowing out of a node is equal to 0, right? So I can just say into right, so into a node is 0. Right, equivalently, we can write that the algebraic sum of current flowing out of a node is 0. Okay, so we have this definition, right, which is sum of the current flowing to a node equal to the sum of the current flowing out of that node, which is equivalent to the algebraic sum of current flowing to a node is equal to 0, equal to 0, and then the algebraic sum of current flowing into a node is equal to 0. Okay, so we are going to use these definitions, right, interchangeably. Okay, now so let's define what we call a branch. Okay, so a branch, what is a branch? All right, so let's define what we call a branch. Okay, so a branch. Okay, so a branch is a connection between two nodes. Okay, so so in short, I could say that a branch is defined as a component connecting between two nodes, right? So component, okay, connected, right, between two nodes. Okay, so what is a loop? All right, so let's define a loop. Okay, so a loop is a closed path, okay, that never goes twice. Okay, so that's the key. All right, so we are going to use these definitions in a minute, so all this will become crystal clear to you. So cannot go and never go never. Right, this is never. That never goes twice over a node. Twice over a node. Okay, so you cannot have a loop that goes twice over the same node. Okay, so now let me give you an example. So let's say we have this example where we have VS1, okay, and let's say we have a resistor R1, and we have another resistor here R2, and we have a resistor here which is R3, have a resistor here which is R4, and let's say we have a current source here which is IS1. Okay, so let's say this is R5, so R5, okay, and this will be R6. Okay, so let's find the nodes and the branches. So this is an essential node, right? So there's like essential nodes. So this is also an essential node. Now we have 3 or more branches meet. This is an essential node. This is an essential node. This is an essential node. Now simple node, for a simple node, I have this is a simple node, this is a simple node, this is a simple node, and it's a simple node. Right, so this simple nodes. Okay, so now what is a loop? Right, so let's define a loop. Now let's give an example of a loop. So this, for example, is a loop. Okay, and this, for example, is a loop. Okay, so we have many loops here, right? So, well, if you like, this one is the outer loop, so I could just go like this, right? It's a loop. I'm going to make space. Okay, but if I let me give you an example that is not a loop. So let's say take so let's say let's find so let's say that I take this path, and I go and I come back, and that is not a loop, right? So for example, I leave this point and I come back to that point, but as you can see, I went through that node, the middle node. I went through that node twice, right? So that is not a loop. Okay, so right, is not a loop. Okay, so you leave a point and you come back to that point, but you cannot go through a node twice. Okay, so now that we have these definitions, let's do an example of let's find some current using Kirchhoff current law. So let's do example. Okay, so find the value of the current Ix. So let's say we have this node, and we have okay, and then we have that. So let's say this is I1, this is I2, that's I3, this is Ix. So let's say that I1 equal to 2 amps, I2 equal to 3 amps, I3 equal to 7 amps, and then we ask to find Ix. So to find Ix, what do? Write KCL. So let's write KCL. Okay, so to find Ix, let us write KCL at node. So let's say that I call this A, node A. Okay, so put in a circle node A. So the KCL says that the sum of the current coming to the node, which is I1 plus I2 equal to I3 plus Ix. These are the current that are leaving the node. So that means Ix equal to I1 plus I2 minus I3. So that is 2 plus 3 minus 7 amps. So this is negative. So well, it's 5 minus 7 amps, which is negative 2 amps. Right, so Ix negative 2 amps. Okay, so now what is the significance of minus in here? So minus is an indication, right? So let me write it down, right? It's an indication, right? An indication that the current Ix right, is flowing into that node instead, right? It's flowing in the opposite direction, right? So it's flowing in the opposite direction as it is labeled. It's labeled. Okay. Now, so that means the current is instead, right? So Ix is instead flowing into that node A, right? So Is is flowing into node A. Okay, so and we are going to use this extensively, right, to solve networks. Please follow me in the next video for KVL.